Hi, this is Dr. Clark, and in this video we're going to learn about vector fields. Let's get started. So what is a vector field? Well, first we want to think about what is a function, and then we'll see what a vector function is. So in this class we've been doing multivariable functions like f of xy equals x squared plus y squared, or f of xyz equals x plus y plus z, or something like that. But you've taken a point in space, or a point in the plane, or a point in space, and then you output a single number. Well, what a vector valued function does is it takes in a point in the plane or a point in space, but it outputs a vector. So an x comma y or an x comma y comma z. So it's going to output the same kind of object as what got input. All right. And the notation we use is capital letter with a line on it, or a bolded capital letter. I think some textbooks like the bold. I usually use the vector notation because you can kind of see the vector on it. But lowercase letters are usually scalar valued functions, and then uppercase, either bolded or vectored, are vector valued functions. Okay, and a vector field is really just a graph of a vector valued function. Okay, and there's lots of examples of a vector field: a velocity graph, like a fluid or a wind or a magnetic field or a gravitational field. Complex numbers are really actually vector fields in a certain way. So there's lots of examples, especially in physics, where vector fields are in play. Although another example might even just be in computer programming. A vector is just an array of numbers, or even an array of words. On websites, you can think of websites as vectors. There's sort of lots of examples, but we're going to kind of focus on ones that you can sort of visualize a little bit. So a vector field, here you can see the wind moving, and then it gets disrupted by this aerofoil here, and then you can kind of see it trailing off, and so you can imagine little arrows pointing where all the wind is going. So maybe here the arrow is pointing this way, here the arrow is pointing up, now it's pointing over, here it's kind of pointing down, here it's pointing up. So at each point you would draw a little arrow where the wind is blowing. Okay, you can see it's turbulent here after this grasshopper, and in this one we've actually drawn the arrows on top. Okay, so when we say vector field, I'm really thinking here's a point in the domain, and at that point the output is this arrow. So this arrow is really what the function outputs, and each point gets a different arrow, right? Each point gets a different arrow, that point gets that arrow, and so this vector is actually the output of the function. All right, and you can imagine, given a x and a y, there's going to be a certain amount of x movement and a certain amount of y movement, and those are the components. In mathematical notation, those x and y components are called p and q. So p and q are actually just regular functions, and then when you put two of them together into a vector, you get a vector, right? So p gives you the x coordinate of the vector, and q gives you the y coordinate of the vector. All right, so a vector field is really a function that spits out vectors, but that function is really just made up of two regular functions. So a vector field is really just two functions in some sense. And you can use either the bracket notation or the ij notation. And then for a vector field to be continuous or differentiable, we just need these component functions to be continuous or differentiable on some region. Okay? Here's an example of a vector field, what it would kind of look like. A radial field x comma y, right? So at each point xy, the vector that gets outputted is the vector xy, so that's going to point in the same direction as where the point was. I've scaled them down a little bit so that you can see them. So really this vector should be much longer, but then they're sort of all on top of each other. So scaling it kind of helps you to see it a little bit better. This is called the radial field because it's radiating out from the origin. X comma y is the radial vector field. It's take the point xy and add and make a vector xy on top of that point. Okay, this is a nice website here for making vector fields. You just use the ij notation and then put whatever function on there you want. And a rotational field, so now I've got the vector field negative y comma x, so that's my That's sort of my P is negative y, and my Q is x. Those are the functions. And when you do that, the vectors, at this point, the vector points that way. At this point, the vector points that way. And you might wonder, well, why would it do that? Let's say I'm at the point 1, 0. The vector must be 0, 1. Because at the point 1, 0, that's 1, 0. Here's up, 0, 1 would be the vector being put on there. And you can see if I'm at x equals 1, y equals 0, then this x would be a 1 and this y would be a 0, and so my vector would be 0, 1. So, and that's going to work at every sort of point all the way around. If I go down here, I'm at the point 0, negative 1, so x is 0, y is negative 1. So then negative y would be 1 and x would be 0, and I get the vector 1, 0. So at this point, the vector is 1, 0, points out to the right. All right, you can see that there. And again, I've scaled them down a little bit so you can see them so they're not all on top of each other. So that's called the rotational field. And there's all kinds of other vector fields. You can put in any equation you want, you'll get a vector field. You can do this in 3 dimensions, but it's harder to graph. Okay, but essentially a vector field in 3 dimensions is really just 3 component functions, a p, a q, and an r, and they each take in points x, y, z, x, y, z, x, y, z, right? So 3 multivariable functions giving you a vector field. So it takes a point in 3 space and spits out a vector. Okay? And similarly, continuity, differentiability, and radial vector fields are defined similarly. If the component functions are continuous, if the component functions are differentiable, then we say that vector field is differentiable or continuous. All right. And now what you might start to wonder is, well, can you do calculus with vector fields? Well, we're going to try to get there. And in later videos, we'll really get there. But I want to just take one idea today, the notion of derivative and integral of a vector field. So the idea I want to tackle today is just the one of gradient fields and potential functions. Okay, so we have seen before that if you had a regular multivariable function, that the gradient is actually a vector field. Right? The gradient of a regular function is a vector field. So that's one way of connecting derivatives with vector fields, is that multivariable functions have a gradient. That gradient is a vector field. And so if you had a vector field, maybe you'd wonder whether it was the gradient of some function. That's sort of a natural question to ask. And we're just going to start with the one direction today. Given a function f, that's called the potential function. If you take the gradient, you get a vector field, and then we'll do some graphs of some potential, of vector fields made from potential functions. Later on, we'll start thinking about, can we start with a vector field and find the potential function? But for now, let's start with a potential function and then find the vector fields. And so you might wonder, well, does every vector field have a potential function? That's a good question. We're gonna tackle that in a later video. Okay, so hopefully that help you see, what is a vector field and what do they look like? How do you make them? And in the next video, I'll do a few more examples so you can see some examples of vector fields. All right, we'll see you then.